Hello viewers, here is Dr. Malada Sharma and I welcome you all to my tiny YouTube channel MALACHEMPHILIC. Today we are going to start video number 107 and video number 107 is the 47th episode of Chemical Thermodynamics where the topic is significance of Helmholtz free energy and Gibbs free energy. So let's start. So first one is the significance of Helmholtz free energy function which is denoted by A. So let's see. First we'll derive and then we'll describe the significance. Right? See, we know Helmholtz free energy function or work function A is equal to E minus Ts, where A is the work function, E is the internal energy, T is the temperature, S is the entropy. Okay. So, our A is equal to E minus Ts. Now, we take the complete derivative of this equation. That means differentiating what we will get? dA is equal to dE minus TdS minus SdT. This one. First function differentiation of the second plus second function differentiation of the first. Now, we know that from first law of thermodynamics, what do we know? We know that heat absorbed reversibly, here you are considering the absorb, that is equal to D change in internal energy and the work done by the system. So, del W reversible. This minus sign indicates that work done by the system will take the negative sign. Right? Now, from second law, we know that change in entropy ds is equal to del Q reversible by temperature in the Kelvin scale. So, TdS is equal to del Q reversible. So now by combining this first and second law, that means from first and second law, what we can write? We can write TdS. In place of del Q reversible, I am writing TdS is equal to dE and then this reversible work done by the system, gaseous system. Okay. Then from here I can write this dE is equal to TdS minus this reversible work done by the system. Right. So, here this one we know. Now, I'll make one demarcation from here to here. Now, coming to this equation. Now, dA is equal to, in place of dE, I can write TdS minus this reversible work done by the system, then minus TdS minus SdT. So look at here, TDS and TDS are getting cancelled. So what is left over? That is dA is equal to minus of this reversible work done minus S dt, right? So what we got? That dA is equal to minus of this reversible work done by the system minus S dt, right? Now at constant temperature, that means isothermal process, dt is equal to 0. So what we can write? dA is equal to minus of this total reversible work done by the system. Total reversible work means mechanical plus non-mechanical. That means work of expansion plus work of non-expansion. So from here we can write minus dA is equal to this total reversible work done by the system. So this indicates that decrease in this work function, it is equal to the total reversible work done by the system, right? So now we'll see the significance of A. So A is such a function that a decrease in its value at constant temperature gives the maximum reversible work done by the system. What we derive from the equation, from the derivation, what we observe. In fact, any transformation, isothermal or otherwise, would always be accompanied by a definite change in the value of work function. Either isothermal or otherwise, there will be change in the work function. But it is only for an isothermal reversible transformation that this change is a measure of maximum reversible work obtainable from the system. So, when it is occurring at the isothermal condition, that means at constant temperature, then only this decrease in this Helmholtz free energy function or work function, it gives the total reversible work done by the system. Now coming to the significance of this Gibbs free energy G. So Gibbs free energy G is equal to H minus Ts, and you know this is Gibbs free energy, Gibbs free energy, and this H is the enthalpy, T is the temperature, S is the entropy. Okay, so G is equal to H minus Ts. Again, we know that enthalpy is equal to internal energy plus pressure into volume, right? So we can write G is equal to E plus PV minus Ts. Now we'll take the complete derivative. That means differentiating. What we'll get? We'll get dG is equal to dE plus PdV plus VdP minus TdS minus SdT. Okay. Now, just now we have derived that from first and second law of thermodynamics, this dE is equal to what we got? That is TdS minus this reversible work done by the gaseous system. Okay. Now in place of this D, we'll put this value. We'll write in the next slide. So dg is equal to dE plus pdv plus vdp. Okay. So dg is equal to dE plus pdv plus vdp, then minus TDS minus SDT. So minus TDS minus SDT. Now I'll put in place of DE. So here DG is equal to, in place of DE, what you can put? TDS minus this reversible work done, total reversible work done by the system. Means total means mechanical plus non-mechanical. Then plus PDV plus VDP minus TDS minus SDT. Right? Now we'll see this here TDS and here TDS are getting cancelled. Right? So what is left over? Left over is dg is equal to minus of this total reversible work done by the system plus PDV, then plus VDP minus SDT. Now at constant temperature and pressure, what we can write? We can write dt is equal to 0 and dp is equal to 0. Right? Then our equation becomes dg is equal to minus of this total reversible work done plus PDV, that is the mechanical work. So this total reversible, dg is equal to minus of this one. So this total reversible work done means it is the mechanical plus non-mechanical. Okay, and this is the mechanical work done, mechanical or work of expansion. This is mechanical means work of expansion, non-mechanical means work of non-expansion, mechanical. Okay, now look at here. So this is the negative of total work done, mechanical plus non-mechanical, and then this is plus mechanical. So this one I can write it as dg is equal to minus of this non-mechanical, total non-mechanical, this is non-mechanical work done by the system, non-mechanical. Okay, right? So dg is equal to, we can write dg is equal to minus of non-mechanical work done, non-mechanical work done by the system. Right? So from here I can write minus dg is equal to this non-mechanical work done. dg is equal to minus of non-mechanical work done. So minus dg is equal to non-mechanical work done. That means decrease in Gibbs free energy gives the value of total non-mechanical work done by the system. Right? So significance of G, what we have observed from the derivation, a decrease in the value of Gibbs free energy function at constant temperature and pressure. You have seen that we made constant temperature and pressure is a measure of maximum reversible non-mechanical work done by the system. Right? And the work function term, that means Helmholtz free energy function and work function, it includes both mechanical and non-mechanical. Okay? But Gibbs free energy, it gives the value of only non-mechanical work done. However, if the system does not involve any non-mechanical work done, if there is no non-mechanical work, then change of this work function will be equal to change of Gibbs free energy function. So what we have observed, that significance of this work function, the decrease in this work function, it implies or it signifies the total work done, mechanical plus non-mechanical, that is work of expansion plus work of non-expansion by the system. Whereas decrease in Gibbs free energy gives only the non-mechanical work or work of non-expansion done by the system. So, hope you have understood. Thank you.